So AFM is part of what is called scanning probe microscopy, and it started in 1981 with the STM, which got invented by or at IBM Zurich in Switzerland. And then two of the inventors went to Stanford in the US, and basically in 1986 came out with the AFM in Carl Quaid's group at Stanford. And Sung-Il Park was a grad student in that group, and he I think immediately saw the potential that the technology has, and everything is history from that point on. He started Park Systems in the US, built UHV STMs, and his first AFM, I think in 1988, so quite early. Then sold the company to Thermo Electron and moved to Korea, where he started the current Park Systems. Park Systems went IPO in 2015 at the Kosdaq in Korea. And maybe interesting tidbit, Park is the only public AFM company. I mean, there are of course other AFM companies, but they over time, the big ones at least, they all got eaten up by bigger companies. Bruker as an example, or Oxford. So Park is really the only company, public company, that does nothing but AFMs at this point in time. So Park offers everything from like a startup research AFMs to inline production, fully automated systems. On the research side, systems are of course very flexible. That's what researchers want. I mean, they do something one day and then come up with an idea, and they want the tool that they buy to be able to help them accommodate that. On the industrial side, it's more recipe driven. Tasks are clearly defined. So that's the product lines. What industries do we serve? We serve basically everything that requires some kind of surface characterization. So it goes from materials research to bio research, coatings, molecules and fluids, energy research, to like the semiconductor industry or the hard drive industry on the industrial side, to just mention a few. And that makes AFMs maybe a little bit difficult to put in a box, because they're so flexible that they can be applied in a wide variety of industries. Mentioned that we are the only public AFM company, and as such, we all live and breathe AFM. So and that shows through our systems and through the way we support our customers. But if we talk about some instrumental features, I think the most outstanding features is that Park looked at the base of an AFM. Basically with the philosophy that if your base is not stable, then everything else you build on top of it, as good as it might be, will always be a little bit shaky, so to speak, because your base is shaky. And our base is what we call the crosstalk eliminated scanner that allows us to do very high performance measurement, such as our non-contact mode, where we don't really touch the sample when we do our measurements, allows us to do a very fast tip approach, recipe-driven data acquisition and analysis on our automated systems. And in general, Park aims to be very user-oriented. Now, everybody says that, but we try to make our systems accessible to a lot of users. And just to give you an example, I mean, you can design a system with a lot of advanced features, but these really don't help you or don't help the so-called average user. And I don't mean that in a bad way, if the user cannot unravel these features. So we really try to look at the user when we design our hardware and our software to make systems accessible to everyone. When I mentioned automated AFMs, I was referring to the inline tools which sits in production at semiconductor or hard drive companies. Research AFMs historically had all these knobs and buttons and complicated menus and adjustments. which were fantastic, but they always gave AFMs basically people always thought like, oh, you need to be a super expert to run an AFM successfully. Now, every decade, Park comes out with a new platform, and what we did with the FX40 is we took some of the experiences we learned over the years with our automated industrial systems and basically put them into a research system. So the FX40 is the first of a new platform of research systems, which hopefully change the perception that AFMs are difficult to use, because they're actually not anymore. AFMs in general are a direct way of characterizing a sample compared to like some optical tools where you need to put some modeling into the analysis. So AFMs are a direct characterization. I mean, what you measure is what you have in general. There are other simple tools. When you look at an AFM and you compare it to some other metrology tools, it's a rather simple instrument. I mean, you have a tip that raster scans a surface in a specific way, and you get a rather direct measurement of that surface. And of course, you can combine it with other techniques, electrical, mechanical, and so forth. Maybe two things that we're tackling in terms of new systems right now is one is AFMs have generally a field of view, so to speak, of about 100 by 100 micrometers. So how do you expand that? And there are various ways of doing that, and we found that the most effective way is to combine it with optical techniques. Optical techniques are fast and they can cover a large range. So we are just releasing an automated tool which combines white light interferometry and AFM in one platform, which basically kills two birds with one stone, so to speak. And then on the other side, chemical ID is always one of the holy grails of scanning probe microscopy, because it allows you to do true chemical identification on the scale of what an AFM can see, which is a few nanometers. And here we are basically use technology based on what was pioneered by Molecular Vista, called photo-induced force microscopy. But instead of making it a research system, we are incorporating it in our 300 millimeter systems for industrial applications, and that is unheard of. There are lots of them, but maybe if I can highlight one that is the application to the energy problem that we have worldwide, and that's also a very satisfying problem. Well, it's not a satisfying problem, but it's satisfying to work to assist in addressing the issue and to hopefully come up with a solution. So how do we generate energy and how do we store energy? So that goes from lithium battery research to like to solar research, to materials research for wind turbines and so forth. So that personally to me feels very good to be part of the solution here, and to be a provider of tools that people use to come up with solution for these problems. And then of course in semiconductor there's also a trend to use new materials all the time, and AFMs are at the forefront there of helping identifying the effect that these materials have on the semiconductor process.